Okay, so we are back, and this is what we had before. So I have a couple of comments here. In fact, I should have a slide. There are two things that I want to talk now, because we did most of the practice. But one question that I like to ask is the GC skew. I should have a slide of that. I don't have it. Sorry. The GC skew. Okay, let's make a slide here. Computer molecular biology, class 5. Okay, this is work in progress. And I have something about for loops, but before, maybe we should start with this one, because I wanted to talk about this later, but I will talk about this now. And I have kind of a computer question and a biological question. If you are doing this course for the second time, you will be surprised that we have not spoke about this construction. This is the way that people do apply in the old times. And I will tell you why it is good and why it is bad. Sometimes we use it, sometimes we don't use it. This is the way that I used to teach it. So you have a keyword for, well, in is also a keyword. Keywords mean that you cannot use for something else because they have a particular meaning, and if you cannot use a function that calls for, or you cannot have a function called function because you will get in trouble. So there are three parts here: an index, which will be a number that we will use to point things, a vector of things that the index will be pointing, and a series of commands. So most of the time, the vector is a sequence of numbers from start to end. Okay, it can be more general, but this is the particular case. The part are index, start, end, and command that should depend on the index. So let me give you a quick example. Okay, it will be very, very silly. Let's close this here. For, it should be a parenthesis, and then we say something like index in 1 to 5, start to end, and then just be careful. I didn't say before, but here we're using these curly braces. Okay, can you see them? That are, well, you have to find in your keyboard. I think in Turkish are on the 8 or something like that. Alt 8, Alt 7 or something like that. This bracket, braces, wrapping around the code. When we use function, we also use them. These braces, these curly braces, like parenthesis braces, are used every time we use code, okay? For wrapping code that we are going to repeat. In a function, all the commands are wrapped there. In a for loop, all the commands are also wrapped there. So let me do this. I'm going to clean. So in the second line, I'm going to say something very simple, print index. And then I can write more commands. Let's say, I don't know, nothing. And then I close the parenthesis, okay? 1, 2, 3, 4, 5. Okay. So this is very much, if you like doing a supply of 1 to 5, and the function is print. Except at the end you get all the result. But the philosophy is the same. So why you will like to use for? I will say two reasons. one, because it's the classical way that people think. I mean, you do it case by case. And the second is because sometimes you are doing what happened here depends on the order that you are doing. For example, you want to go from the first gene to the last gene and looking which is the largest one, for example, or the smallest one or something like that. Remember, this lapply and sapply work in any order. They are essentially doing everything at the same time. They are doing number 1, 2, 3, 4, 5 in any order. There is no guarantee that you go from the first to the last. If you want to make sure that you're going from the first to the last in order, you have to use the for loop. Okay? Then, in the last semester, let me close this one, not relevant anymore. In the last semester, we also did this thing here. If we want to do the same as sapply, we will do something like this for E, and here we are using the function. Let me show you what is the problem here. I'm going to give you later more detail about this, just trying to give you the first idea, because some people are doing for the second time, and I want to compare the classical way with the modern way. They both have advantage. Sapply, for example, is fast. For is slow. But sometimes you want to go yabash, sometimes. So, for example, we want to do what the other code, this one, complete code for I want to. So you see, it's very similar, but it takes longer and didn't show anything because we are not assigning to anywhere. We are not doing. We want to assign. So, what will we do if we want to do something like sapply? When we apply the function, we got a result that is a vector. We want to create a vector and store the result in the vector. How we will do that? Well, what we usually do is what we have a vector that I like to call answer. That will get the answer of the command. Okay? Are you with me? But then we need to use an index, because this is going to be a vector number 1, number 2, number 3, number 4, number 5. Okay? So answer. So the gene number 1 get answer number 1. Gene number 2 get answer number 2. Okay? I am trying to get something like this, GC of all content. I am trying to recover this. Okay? But not using map, not using sapply. I am trying to get it one by one. Are you with me here? Are you following my reasoning? Okay, let's see what happened. What will happen is that it will say, I don't know what you're talking about. There is an error here. So
we should do answer equal to parentheses, but
yeah, something like that. We should. We need to have it. Let me go one step. I can assign something to answer, but if I use brackets, this is the point that I want to emphasize. If I use brackets to assign, then this vector should exist before. If we talk about a vector that doesn't exist before using it, the computer will say, what are you talking about? I cannot put a value inside a vector or a list, or I mean, the computer cannot know if answer is going to be a vector, a list, or something else. So that is a problem that we have to handle. We have to first create the vector before using it. If you are going to use brackets, if you are going to assign to the content of the vector, you need to create the vector before. So the rule that we used in the last semester was this. I say answer. I created like a vector. Now, I don't know what should be in that vector, so I want to say something like NA. Bilmiyoruz. Okay? We're going to make a vector that we don't know. Well, we know something. It's one element for every gene. So we know that their length of gene. 4,000 of this. So I have essentially to repeat NA for the number of genes. Okay? This is the formula that we use. We are going to use it. Not very much, but we are going to use this. This is something that will be used for later. Let me make this small because we don't need. Let me show you. So we don't have answer yet here. What I'm saying is that let me remind you the command rep. Let me remind you the command rep is some of the way in the first class we say how to make your own vector replicate element of vectors and lists. So there is you have sequence and you have repeat. So we are going to repeat NA many times. How many times? 4,000 times, 4,140 times. Okay, let's do it very quickly. So it's a logical whatever. So you have NA, 4,140. Okay. Now, after we created, you can do the for, and now there is no error. So we have to create, and if you see the numbers are the same. So let me put it side to side. And so the correct command here is something. Okay, let me do it the correct way. I'm going to history and I'm going to copy these 4 lines to the source code here. And there is something that you may have seen that I do. This is optional, but very much recommended. Every time that I open these braces, everything that go inside the braces, I put it in with a tab. Okay? That is a convention. And in Python, that is mandatory, for example. In R, it's optional, but it's very much recommended because it allows you quickly to see what is happening. And in fact, we used to before. Let me show you. In the here, for example, you see I say function, I put braces, and everything that I put inside, I move it. So you can see quickly when the block starts and when it ends. So it is optional, but very much recommended. For example, here, again, you see that I start, every time I open a curly brace, I go, I don't know, 4 letters inside. I just tab. So if I have another parenthesis, another brace, I will put more tabs, more tabs. It helps you to understand what is happening, when blocks start and end. Okay, it's a visual thing. So I did it here. Let me put more clear. So the complete code you have to create. So and you have to compare with the others. So in previous semester, this was the way that I teach. You create an empty vector, then you have a loop from the beginning of the end. Notice that this number, let me write, notice that length of genes is used twice. One to create a vector and one for the for loop. So the summary for now, the summary is that supply is much easier. So instead of these 4 lines of code, what I'm writing here is simply, let's say, where 2 and where 2 to not confer supply. And look, the parts are the same. I have the output vector. I have 1 to length. This will be my input vector. And then the function. Ah, interesting. Okay, let's make in 2 parts. Okay, let's go to the problem here. There is an error here. I will try, and we will see that there is an error. And I will ask you to find the error here. It says there is no, it's not a function. Okay, I will spend 5 minutes in this part, and then we go to a more biological question. Okay?
Can I ask something?
You always ask if you can ask something, and when you ask that, you prove that you can ask something. So just ask.
Okay. Can we use a pipe in this function?
Yeah, we can. We can. The point is this. The point is this. It's an interesting question. All the pipe thing that we used in the last semester were essentially vector to vector. You take or more like data frame to data frame. The pipe was like you take a data frame and you get a new data frame. And here we are not using complete data frame. We are using vectors or sometimes just single values. So you can, but they are not necessarily the best tool here. In some sense, we are using more low level. What can I say? Pipes are kind of the big picture. You are doing with big tools, a very macro level. You are looking at the problem from a very high perspective. Here we are kind of going inside and we are looking like one by one. So yeah, at the end it will be, but here we are kind of opening what is happening inside that pipe.
Okay, thank you.
So 1 second, I want to show you two questions here before we're going, and I hope you don't get more confused. I hope. Number 1, this doesn't work. As you see, I got an error here because this is not a function. Click here. This code is not a function. Why do you mean that it's not a function? Well, GenGC content is a function. Like square root is a function. But when you use the parentheses, then you are meaning the value of that function. And the value of the function is not a function. Square root is a function. Square root of 4 is not a function, it's a number. Okay? So here we need to do something different. We need to get rid of these parentheses somehow. But then the result will be wrong. We get only zeros because here we are getting numbers and this GC content was expecting vectors. Vectors, exactly. So let's make it short. I don't want to get too much. I don't want to give you too much noise now, but I will use the old function. The function 2 here will work better. And now we got the same values here, okay? So we are going to talk about this later, but I want to go more to the exercise. So here I'm going to use GC content, the version 2. Let's use version 2 here to be coherent. Okay, I have a different question here, and let me see if I have some slides, but I will give you one. In fact, let's do it here. Let me Google for GC skew. GC skew. Okay, let's go to Wikipedia. I have some slides, but I don't have them at hand right now. So, do you know anything about GC skew? I mean, a biological question. I mean, you can say yes, you can say no. All answers are valid here. Yes, say yes or no. GC skew, GC bias, maybe. This is the formula. No, no. Okay, fine. It's just a question. Just not everybody got the same class. Okay, GC content, GC. I'm trying to find if I have the because okay, here I have the slide. Okay, I will show you all the slides if I have them at hand. Maybe I have them at hand and will be faster. This was my class 10 of last year, but I will give them an updated version later. Okay, 2020, computer molecular biology 2, class 10. Do I have it here? Yes, and we spoke about GC content, and you see the formula that we have before. And well, the thing that okay, GC skew. What is the size of G minus C respected to the total G plus C? That if you saw here in Wikipedia is what they say here. G minus C over G plus C. And I will show you the end of the point. It's because of this. Again, about replication origin. If you see what is happening here, the first part of the genome, there are more G's than C, and then around the origin of replication, you tend to have more C than G. Did you know that? In bacteria, this is true in bacteria, not in archaea, not in eukarya. In bacteria, you have this thing that half of the genome has more C than G, and the other has more C than G. And the break. What do you mean? That the DNA is not symmetrical. It means that one part. Okay, a good question. What is the meaning of this? It's a very philosophical question. It means that evolution through the constant replication, let's say through the constant replication of the cell, there is some bias to keep G's in one side and C in the other. Now the question will be why it is. And the hint that I'm giving you is that the origin of replication, or it's connected to this point with the sign change. When you go from positive to negative, that is the origin of replication. So let me see if I have, that is what we got here. Let me see if I have the explanation. Yeah, here. No, this is not a good plot. We are not going to do the plot. People do this. No, this is not a good class. Okay. Okay, I will give you the good slides because I didn't expect to teach you today. We went going faster than I expected. Look, this. They do it here for different bacteria, and they have same kind of patterns in many bacteria. Mechanism. There is a lot of consensus, but there is the idea that let me see. I have some slides that even a nice picture of this. The basic idea is that during replication, I don't have HTML. During replication, one of the strands, when the DNA opens, one of the strands is exposed to the environment more than the other. Let me go to the important point here. Here, this is the one that I wanted to show you. When the cell replicates, the DNA opens in two strands, okay? And you have the polymerase, the DNA polymerase going from 5' to 3' and same in the other direction. So there are two polymerases acting like this, okay? And the point is this: when the polymerase is acting, one of the strands is going directly and getting replicated. One of the strands is going 5' to 3' and is getting filled immediately, and the other is getting filled step by step, because it kind of need to be attached again and again. Yeah, this one. Let's see if we have. I hope you can see this video. Otherwise, I send you the link. I hope you can see it. I don't know. Did you get the audio? No.
No audio.
Okay, let me see, because I shared the screen without the audio. But 1 second. So new share, same screen but share sound. Wait. Optimize for the clip. Okay. I'm turning off my camera in the meantime.
DNA is a molecule made up of two strands, twisted around each other in a double helix shape.
Can you hear now?
Each strand is made
Yes.
up of a sequence
Good.
of 4 chemical bases, represented by the letters A, C, G, and T. The two strands are complementary. This means that wherever there's a T in one strand, there will be an A in the opposite strand, and wherever there's a C, there will be a G in the other strand. Each strand has a 5' end and a 3' end. The two strands run in opposite directions. This determines how each strand of DNA is replicated. The first step in DNA replication is to separate the two strands. This unzipping is done by an enzyme called helicase and results in the formation of a replication fork. The separated strands each provide a template for creating a new strand of DNA. An enzyme called primase starts the process. This enzyme makes a small piece of RNA called a primer. This marks the starting point for the construction of the new strand of DNA. An enzyme called DNA polymerase binds to the primer and will make the new strand of DNA. DNA polymerase can only add DNA bases in one direction, from the
This is the key
5'
point.
end
There is one
to the 3'
direction.
end. One of the new strands of DNA, the leading strand, is made continuously, the DNA polymerase adding bases 1 by 1 in the 5' to 3' direction. The other strand, the lagging strand, cannot be made in this continuous way because it runs in the opposite direction. The DNA polymerase can therefore only make this strand in a series of small chunks called Okazaki fragments. Each fragment is started with an RNA primer. DNA polymerase then adds a short row of DNA bases in the 5' to 3' direction. The next primer is then added further down the lagging strand. Another Okazaki fragment is then made, and the process is repeated again. Once the new DNA has been made, the enzyme exonuclease removes all the RNA primers from both strands of DNA. Another DNA polymerase enzyme then fills in the gaps that are left behind with DNA. Finally, the enzyme DNA ligase seals up the fragments of DNA in both strands to form a continuous double strand. DNA replication is described as semi-conservative because each DNA molecule is made up of one old, conserved strand of DNA and one new one.
Okay, and then something more nice. Okay, so where are my people? Let's stop sharing. Okay, I see you again, and you don't see me. My computer gets very hot when I do this. So, okay, I hope you saw the video. I mean, unless nobody say we cannot see. But the key idea is that this lagging strand is exposed to the environment. I mean, this is the explanation I know, but you can read more about it. So since one of the strands is more exposed, then there is a point that the guanine molecules are exposed to some mutation and they become cytosines. They can lose something and some part of the structure and become cytosines. So, of course, some of that mutation can be very bad and the cell will die and you don't see it anymore. But if the cell can survive, then it will still be there later. So what it means in practice is that the leading strand will tend to have more G than C, and the lagging strand will tend to have more C than G. And the way to measure that is to measure the GC bias, or the GC skew, if you like. Okay, so let me share again this thing. So something like this. Okay. Here I did something a little more complicated, but right now I'm just proposing this simple exercise. What I'm saying is this question of the contrast between G and C is a good question biologically. Okay, it's not something that I inventing because it's beautiful, which is beautiful, but it's not a toy problem. It's a real problem. It's something that when you get DNA that you sequence and you want to know what is the replication origin, you do this thing. And in fact, it's a test of the quality of the assembly. If the DNA is not correctly assembled, you will not see this, and it's a kind of quality control for bacteria. So, and when you are looking for horizontal transfer and things like that, this is also something very, very critical, that you expect to see this, and if you don't see, you know that something happened. So how we do that? So my basic question is how to calculate the GC bias. the GC skew. GC skew. Let me how the function. What is the function here? Not in this slide. Ah, this one. Okay, this is a different question. No, sorry. Okay, let's write it here. So let me write, we are saying GC skew, and the formula will be, so I want to calculate gene by gene to see which genes are in the positive side, which genes are in the negative side. Okay? The formula is, and I will write the mathematical thing here, as the fraction between G minus C divided by G plus C. A and T don't count here. So let me do the knitting. What is the option here? Preview, no preview. Yeah.
You didn't write divided by.
Sorry?
You wrote wrong, I think, because you wrote G minus C, then G plus C.
Yeah.
It is not divided by.
I don't follow you. But look, let me, what I wrote here, this is the result that I show you here. Okay.
Yeah, I get it. But I want to say you didn't write divided by symbol, same symbol.
Ah, no, the way that I wrote, I was using a different notation. But the point is that, look, the divide is here. I didn't write it in R. I wrote in a different, I mean, we never teach, but in Markdown, I was writing in Markdown. In Markdown, you can write mathematical formulas. And I wrote the mathematical formula to look like this, like a fraction. Okay?
Okay, thank you.
Yeah. No, I see your point. I see your point. But I was not writing R. I was writing Markdown. So it looks correct. So, and the same that they wrote here. Maybe this is more clear, but okay. And in fact, people can calculate also AT skew. And the interesting thing, if you do with AT, you don't see. You can compare C to A, C to T, A to T, A. You can make all the combinations. And in general, they don't have anything in particular. But GC is super clear that it goes from one side to another. Okay? So let's do this thing. How we will do this? This is the exercise for today. How we can calculate. And if we do in half an hour, we finish early. So let me show you again. You see the formula here. Well, the first thing that I recommend is that we recycle we already solved for one case for the GC content. Let's try to adapt. Let's no even before. Sorry, let me go back one step before. Write it in English. Before recycling, write it in English. You can look at the old English, but if you want, write it in Turkish and then you translate to English as you feel better. But how we solve this problem? So I will say this is first for each Gene. We will go gene by gene.
I wrote something from chat, but I'm not
Ah,
sure.
okay. Okay. Chat is welcome here. Yeah, the GCSQ. Yeah, okay. You have something, some funny notation, but yeah, fine. Okay. That's why it is better that we write. Let's take a minute to write it in English before going to R. And to be honest, I am very much in this philosophy now that write in English first, like write for human, write for human, and then you write for the computer, because the computer will do whatever you say, and it will give you something that may be right or wrong. But if you don't write it for human, you are not sure that you are doing the correct thing. Okay, so let's write for in English. How we solve this problem? Calculate GCSQ of each gene. For each gene, we do separate. For each gene, we don't need to do all genes at the same time. That is the first step in the problem, that we don't need to do all genes at the same time. We can think one gene every time. Okay? Agree? Yes, no?
Yes.
Then what do we do with each gene? What is the first thing that we need to do? I mean, let me show you that we had this question before. We talked about this in the homework. No, in the homework. The class, we did a Google document. Do you want to see the Google document? What is the first thing that we have to do?
We should download data that includes.
Okay. But this probably before. Okay. The gene of E. coli. I'm putting in italics here. Fine. But we did already. So problem solved. Then we have a list with every gene that we also solved. How we calculate G minus C? How you calculate this formula?
We should count the C and G.
Exactly. Count C and G. That we already know how to do. This is and this is the code, no? Let me write it like a code. Will be C and then will be G. This will be the code. Let's put the spaces when they have to be. This is like, okay, let's call it V as we called before here, the vector for the sequence. Something like that, okay? And then, after you count,
we should find the formula, write the formula. G minus C divided by G plus C.
And put the parentheses in the correct place.
Yes.
I'm writing like this is the formula. And finally, we return the calculated value. Okay. That is the English version of this thing. So the thing that we do for each gene the thing that I put kind of with space at the border is going to be a function. So let's write a function. Okay, I want to write it from 0, but I think you will remember what we did before. I mean, I'm trying to recycle it there. So how will we write? I'm putting here R code, and what will be first? What do you need for a function? Remember this. This is what I wanted to get here. The today class. What do we need to write a function?
Command and
Command, okay.
return output.
I said every function needs 4 parts. Slide number 15, I think. Remember slide number 15.
An input also.
Exactly. We need to find the input. This is a slide that I want. This one. We need to find the name. What are the input? What are the commands? What are the output? Okay. The commands, we have it more or less clear. We need to define this thing. Okay. This is the part of. So what will be the name? What is the name of the function?
GC skew of all genes.
GC skew of genes. Let me make it a little. Functions are doing something, so I want to put a verb. I will say calculate GC skew. I suggest this name. Okay. Because if I say GC skew, I don't know if that is a function that calculated or is the result of that calculation. So I prefer to put a action very clear. And then I have one comment here. I want to comment that these are underscore. You cannot put minus sign here, okay? Don't make this mistake. You cannot write like this. This is wrong. It will not work because this hyphen tire will be like minus sign. You should use underscore. You can also not use a space. Try to use this underscore, okay? Then we put an arrow, then we say function, and then we get the input. What will be the input here?
E.
Let's call DNA. It can be V. I agree. It can be anything. In fact, it can be anything. But I prefer to call it DNA because I want to do something with it. I want V to be the uppercase. Remember that we need that step of making it uppercase. And I open the brace. Let me do it again. So the function has this part. Let me show it again. Name, the keyword function, then some variable. It can be V. It can be anything. It can be anything. But you have to be correct. Okay. And then this funny parentheses, braces, curly braces, and then the comment. So let's open the braces here, and you see it open and close automatically. And here, following the convention, I will put tab to make it clearly that it's inside. So what are the commands? Well, let's follow the same that we had before. Okay, let's be lazy, and we copy the function that we have here, something like this. In fact, it should be like version 3. We say that this was better, no? Something like this. But now we are going to be more careful here. this is fine. We get the letter. Sorry, everybody understand why we have to do this step, no? The to upper. This is a technical thing, is that some people write DNA with lowercase, some people write DNA with uppercase, and we don't want to get into trouble. So here you put whatever you like, lowercase or uppercase, but our V inside our function is only uppercase. We guarantee, because we took it and we transform every lowercase to uppercase. So this will always work. Count V, count C. Instead of GC content, we want to get GC skew. And this is GC skew. And we want to use the formula here. What is the formula? This one here. So I will be very lazy. I'm going to copy this one. Like this. Closing this. And let me copy and paste this in our screen here. And we get this calculate GC skew. And let's see what happened. How we use it? Calculate GC skew of, for example, gene 1. And it's not gene, genes plural. That is my error. Let me show it again. This is the way that we define the function. If you see, it is not very different from the one that we did before. The only change, if you see, the only change that we did is that we put a minus here instead of a plus, and we divide by the sum instead of the total. Okay? Why we use this formula? Well, essentially, you have to answer. One is because in the literature is the formula that people use. But the second reason is because we want to compare C and G and nothing else. We essentially, for this formula, we don't care about what else is happening with A and P. We are only seeing the competition, like from the total of G's and C, how many of them are C, how many of them are G. For example, if all letters are, sorry, this is, I'm doing it backwards. This is G and this is C. Okay, because this is important, no? G plus C. Not C minus G, is G minus C. Okay? Fine, that's correct. We are making them compete. If all is G, this number will be 1. If all is C, this number will be -1. If they are equal, then this number will be 0. Okay, it's kind of a measure of which side you. Fine. Now, how we do it for everybody, for every gene? I don't know if you are there or your people got frozen. I have only one question for you. We did it now for the first gene, for the second gene. How we do for all genes?
You should write calculate GC skew parentheses 1 to length of DNA.
Well, first we don't have DNA here. The DNA, notice that, look here. Here is all the thing that we have. We have chromosome, genes, genome, but we don't have anything called DNA. DNA is something that exists only inside the function. Maybe you should take a minute to realize that. Inside the function, you can have your own variables. I don't know if Dilem is asking a question or being very happy of the explanation.
Yeah, no.
Okay.
No, I was just gonna ask a question.
Go.
So should we just write genes for calculating all of the genes?
Well, that is a good guess, and the answer will be. Let's see what happened.
Oh, nothing.
No, it is worse. It is kind of working a lot.
I wrote something from chat.
Yep. It took a lot of time and say, no, this doesn't work. Yeah. Let me remind you of the class in the morning, and that's why I say you need time to process. The summary say, Lapply and sapply are great. We essentially need, I want to rephrase, we want to apply the function that we calculated over all genes. Remember, here you enter with DNA, not with an index. This is DNA. So if you want to use the same function over each one of the genes, the simple way to do is to use sapply. Let's do it. Apply the function and give me a simple answer. Remember, the S is for simple. Simple apply. Simply apply over each gene, over all genes. Let's read like that. Simply apply over all genes the function calculate GC skew. Okay? Simply apply. And this is going to take a minute and going to give a lot of numbers, more than we care, really. So let's, in fact, we don't want to print them. We want to save them. And this is what we're going to call GC skew of genes. Let me clear the screen for you. GC skew of genes will be applying over all the genes the function calculate GC skew. Okay? GC skew, we got something, GC skew of genes here. Let's plot. Interesting. Interesting. Do you see the change of sign? No, it's not clear, the change of sign. Interesting. I didn't expect this result, to be honest. I didn't expect this result. So there is an explanation for this, but it will take longer. So you may ask, did we make a mistake? Maybe, but I will say, I don't think that we make a mistake. We see that in general, we are going around 0, but more tending to a positive value. What is the GC skew of all the genome? Calculate GC skew. I mean, in other words, what should be the average here? What's GC skew of genome of E. coli? In global, through all the genome, and it's a very small number. So we can draw it. So this is, I find it very interesting. The GC skew of the genome is more close to 0. They are very balanced in total. which should not be a surprise because in general, every time you have a G, you have a C. And every time you have a C, you have a G. Okay? In general. But we have that genes have a bias different than the genome. There are a few that are negative and a lot of that are positive. Why? Okay, I'm not expecting an answer right now because it's a longer answer. But it's super interesting. My point is this. I expected these genes to be either around, you remember like we did before when we had this the GC content of all genes, they are all around the average of the organism, okay? But the skew is not around the center, you see? It's kind of shifted. That is surprising. I will answer that next class. If you like, because I'm saying that people are sleeping now. And I don't want to get too many in biological detail. I want to kind of wrap the idea of today's class. So let me write the code here in the slides, and then using the function. Using the function, we go to history here. We did this thing. We say calculate supply. This one and this one. And let me do, and we show here in the slide here. Ah, made a mistake here. You see an error in my code. 1 second. Let's fix it. Why because I wrote here, write it in English, probably the space here.
R should be in curly braces, I guess.
I am making a trick here because okay, let's do as you say. The point is this. I am just writing the code, I'm not evaluating it. So because if I want to do it completely, I need to load the DNA. So let's start with loading the DNA. That is the part that I'm missing here in this document. Let me see here. So let's take the old code that we had from previous class. From the previous class, we are going to do this. We have the read FASTA from the very beginning of this class. R, as you ask, library sec in R. I am loading. You will have to use the correct path here. And we are asking the length of gene here to see. So here we have genes. Then let's calculate using supply, but we need the old function. The old function, I will call it not this GC content version 3. Well, old function is not the GC content function. The function to calculate GC content was this one. Let's write it here. Pum, pum. Close it here. As you see here, it is not very easy to see when it starts, when it ends. So I am doing 4 spaces. And now it should work. This work here now. It will take forever, but okay. And then the supply version with the for. Okay, let's see what happened now. We want this to be also a function. Let's see what happened. I'm not sure this will work or not. So what I was doing, I was writing the code without executing it. That if I didn't use the curly braces around the R, then the code is not executed. And it, as you see, was faster and I didn't get any of these warnings. But the summary is this: function, apply. Okay, supply, sapply. And if you want something else, for. I will speak about for more in detail later, but this is the result that we got. I still have an error here. But the result that you have to keep in mind is this. This is the old way, let's say, or the step-by-step way of calculating a result. You create a vector and you have this construction, a for loop, and you do it one by one. The fast way is with supply. You can compare. I will put these two in the same slide. Let's put in the same slide. But this is one line. You have the start and end and the function. So you can have a for loop that takes 4 lines at least, or you can have supply that takes 1 line. The trick is you need to have a function. That is the trick. So most of the time what you want to say is, what is the function here? What is the function that I need to repeat? And for finding the function, the idea was to recognize the pattern. For the GC content was easy because we already saw the logic before. And when you get the function, you can calculate this. I'm doing it wrong here. Okay, let's finish before I make more mistakes here.